Yeah, so can you hear me? Good. Yeah, thanks for having me. So I'll be continuing the talk of yesterday by Professor Lubotzky, but I'll revise and redefine everything. So he gave a more of a big picture idea. I'll go a little into the details, not too much. I'll give you an idea of the tools and the techniques used. So for the first part, I just wrote it down because a lot of epsilon delta definitions. It's just easier to look at it rather than write everything down. So the question of stability is, when is an almost homomorphism close to a homomorphism? Now, of course, every word here has to be clarified. Firstly, what's almost? And for almost, we have a kind of a local definition. That is, we take all possible pairs of elements x and y and ask how far is phi of xy from phi of x, phi of y. So if it were a homomorphism, it will be equal. Distance would be 0. So G is some target group which comes with a bi-invariant distance. So this is a kind of local notion of how far it is from being a homomorphism. The other, close to a homomorphism, is a more global notion. It says that, okay, how far is it from some homomorphism? So you take the infimum over all possible homomorphisms, that is the closest homomorphism, and just take the distance. So these are all like L infinity, supremum distances. So you have two notions of distance from a homomorphism, right? So one is a local called the defect, and the other is a global called the distance. We'll just call it the distance. And the natural question now is, how are these two related? Like, firstly, it's easy to see just by a triangle inequality that if the distance is small, then the defect has to be small. You just do two steps of a triangle inequality here. So the more interesting question is in the other direction. If the defect is small, if it locally resembles a homomorphism, does it mean that there is some homomorphism close to it? This is a non-trivial question, and this is a kind of question that is often encountered even in, let's say, computer science, for instance. It's called property testing, where you have two notions of robustness, and you want to relate the two. So a positive answer to this question, that is, if the defect is small, then the distance is small. If you can have some statement like that, some robustness or rigidity statement like that, that's called uniform stability. Of course, it's uniformly stable with respect to this group, with respect to that distance that you use. So gamma is uniformly G stable if, given any closeness to a homomorphism, there exists some small enough defect such that this almost homomorphism is close to a homomorphism. This is the usual epsilon delta definition. But you should just think of it as, you can make the defect small enough so that beyond that the distance will be small. So almost okay, the most natural is you take a homomorphism and disturb it. We'll come to an example of, you want an example of an almost homomorphism that is not close to a homomorphism, right?
Close to homomorphism, but we can write it in a natural way where almost homomorphism.
Well, I don't know about natural in the sense that often this is a question of error. For instance, in computer science, it's like error correcting codes or something. There's some corruption, and you're asking if that corruption can be corrected to get something, a true one, close. So I think that's a better way of thinking about this rather than an almost homomorphism arising. But we'll see examples of some clever constructions where it's not close to homomorphism. But this is just a definition so far. We'll get into it in more detail, but there are some more general notions. Yeah, we'll come to that immediately now. So this is just choosing a larger family over which you can give these universal parameters. That is, this is for one particular target group G. Usually you want to do it for a family of groups, so that for any group in that family, you have the same epsilon delta parameters. And why that is useful is because in our setting, for instance, we'll always take this capital G to just be the set of unitary groups with some nice norm, a submultiplicative norm. We'll see why later. But we'll just think of almost representations rather than almost homomorphism. But this is a general setting. And this setting, you can change this G in different contexts to get different objects of interest. For instance, as was pointed out in the lecture yesterday, you could take it to be the symmetric group, and then that will give you connections to sophicity and group approximations. But for us, it'll be representations. G will just be the unitary group, UN, for some n. And so this is just parameterizing over the family. And finally, a stronger definition is that it's not enough if epsilon and delta are small enough, but there should be some linear relation between them. That is, once you have the defect small enough, after that, the distance should just be a constant times that defect. This is a much stronger, much more robust notion of stability. Again, just definitions so far. So, any questions about what the question is? So when did I start? I just want to keep track of time. Okay, perfect. Okay, so this is the most general and precise definition of the question, but the most natural toy example you can play with is called a quasimorphism. Quasimorphism is some question like this in a much nicer, simpler setting. You just have a map from gamma to the reals. No group, no metric, nothing. Gamma to the reals, and it's a quasimorphism if a similar condition. If f of xy minus f of x minus f of y is bounded. So it is, in some sense, the same question, but here the target ring is R, so it's all linearized. Instead of phi of x, phi of y, it becomes f of x plus f of y. So if a function f has this condition that it's not exactly a linear map or a homomorphism to R plus, but it's still bounded. Locally, it still looks like almost like a homomorphism. So this is called a quasimorphism, and this looks like a simpler setting of this, but in fact, this is still an object of study. It's a very interesting question whether you can have quasimorphisms for gamma. What is a condition on gamma that allows it to have quasimorphisms? Well, of course, it has quasimorphisms in a trivial way. So let's denote Qm. No, it's not positive numbers. It's additive reals. So Qm of gamma is the space of all quasimorphisms. It's a space because you can see that it's closed under linear operations. So can you give an example of a quasimorphism? Again, as I was telling him earlier, a trivial example is the set of all homomorphisms and just disturb it by some bounded function. These are the stupid examples. In fact, it's a direct sum, because if you take gamma to be infinite, you're not going to get a bounded homomorphism. So it's a direct sum. So this trivial quasimorphisms, we actually call this trivial quasimorphisms. This is the formal definition. Trivial quasimorphisms. So the more interesting question is, are there non-trivial quasimorphisms? That is, can you actually have functions which aren't just the boring technique of just taking a homomorphism and disturbing it? So that's the, so the question is this non-empty or not? That's the more interesting question. So this already hints at some sort of cohomology that we'll develop in this toy setting first, just to motivate the more general construction. So f is the function that you start with, and look at this as a function. This actually looks like a 2 co-cycle. Actually, it looks like a 2 co-boundary, in fact. So this actually looks like d1 of f. d1 of f of xy is f of xy minus f of x minus f of y. I think usually they write it as f of x plus f of y minus f of xy, but there's no difference. So this is actually, so d1 of f, if you notice, is actually a cycle. So it's a bounded function. d1 of f is a bounded function, which, and just a sec, I'll write this and then I'll explain. So what have I written here? d1 of f is a bounded function, which is also a co-cycle, because if you take d2 of this is going to be 0. So it's the kernel of d2, but also bounded. This is the notation here. But it's also a co-boundary in the usual sense, because it's already written as a co-boundary. It's just that we don't know if it's a co-boundary of a bounded function. And that's the question here. Because if you could write d1 of f as some d1 of some beta, where beta is a bounded function, then f minus beta will be the homomorphism that you're looking for. So that's the idea here. You take this quasimorphism and you just take the defect map, the d1 of f. You see that it is a bounded co-cycle, which you're hoping is also a bounded co-boundary. So in a sense, where this d1 of f lies is called the kernel of the comparison map. So I'm just assuming some basic group cohomology, just a definition, of the functions and the boundary maps. So, but it's all in just degree 1 or degree 2. So if you have any questions, just let me know. So I'll just tell you what this is. So what this comparison map is, just a forgetting map from bounded cohomology to ordinary cohomology. So bounded cohomology is just a restriction of the usual cohomology to bounded maps. So it's like a functional analytic analog of the usual group cohomology. Instead of just taking it to some abelian group, the coefficients have a norm. So you can actually talk about bounded maps. So here, what you notice in this very simple setting, we're just complicating it by putting it in a framework that is standard, which is saying that d1 of f is actually an element of the second bounded cohomology, which vanishes in the comparison map. And what the comparison map is, just a forgetting map. You forget that things are bounded. So what the conclusion here is that the question whether there exist non-trivial quasimorphisms is related to the question of whether the kernel of this comparison map is 0 or whether the comparison map is injective or not. That's so far it's just some observations. So this is just to give you a hint that quasimorphisms and even the epsilon homomorphisms, in some sense you can hope to put it in the framework of cohomology because the defect or the problematic parts look like some sort of a cocycle. At least in the toy setting, it's very precisely a cocycle in a nice way. And this is actually studied in much detail. So now notice that if the comparison map is injective, then there are no non-trivial quasimorphisms. This kernel C is 0, which means that there are no non-trivial quasimorphisms. That means that D1 of F is D1 of beta, where beta is bounded, so F minus beta is the homomorphism that you're looking for. And if the H2 gamma is 0 also, you're happy, which is often what you'll try to do, because instead of computing the comparison map being injective, you could just hope for the cohomology itself, the bounded cohomology, to be 0 and you're happy. So this hints that you should try to capture the defect in some sense as a cohomology. So as I was saying, if H2 bounded of gamma R is 0, then gamma has no non-trivial quasimorphisms. This is just an observation. Okay, now time for examples. What would be a good example of this being 0? Well, the classical boundedly acyclic groups are amenable groups. So I'm assuming that I don't have to define amenability. Everyone knows a definition of amenability here. But for us, the definition will be the existence of an invariant mean. So the invariant mean here actually can be used to show that H2 bounded is 0. For instance, over here, you can do it very directly. So you're given D1 of F. How do you get the beta that you're looking for? Just do an averaging. You want D1 of F of xy equals d beta of xy. So how will you define beta? Just define beta of x as the amenable averaging of d1 of f of x g over g. So you're just locally averaging around, and this will actually give you. So if you now take d1 of this, you can go inside and you can see that d1 of f is equal to d1 of beta, and beta is bounded because this whole thing is bounded. This is a standard method of showing that amenable groups have vanishing bounded cohomology. Here it's reals, but you can even do it more generally. But the idea here is that for amenable groups, you can both show the vanishing of the bounded cohomology and our stability thing in this quasimorphism setting directly. Just take an average. It's always there for you in amenable groups. So the first conclusion is that amenable groups have vanishing H2. So in particular, it also has no non-trivial quasimorphism. The other is a more interesting example, and I'm not going to prove it. It's nice. It's something fun that you can try to work out. F2, the free group, has non-trivial quasimorphisms. This is the example that you were asking. And what is the construction? I'll write it down, and I don't have the proof here, but it's not hard. So let's say F2 is generated by x and y, and you have some word like this: x to the n1, y to the m1, x to the n2, y to the m2, dot, dot, dot. So I'm going to define f to just be over all this t sine of nt plus sine of mt. So you need to check two things here. The first is that this is a quasi-morphism. For that, you just have to take f of some two elements minus f of that and f this, and then you need to show that this is far away from any homomorphism. It's an interesting homework, but it's not relevant to us right now. But so you immediately notice something here, that this quasimorphisms, it's trivial for amenable, and there are so many for the free group. So it's the usual, the spectrum there. On the one hand, you have amenable groups where everything is nice, and then the other extreme is a free group. And somehow you also see that the cohomology gets involved. So this is all for just quasimorphisms, which is functions from gamma to reals. But we are interested in functions to the unitary group. So is there a connection between quasimorphisms and functions to the unitary group? There is, at least for U1, which is just a circle. And the connection comes through the usual trick, just take exponent log. So this, I'll state this. This is again something that can be quickly checked, which is that if f is a non-trivial quasimorphism, that is, it's a function to R which is has bounded defect, then you can exponentiate it to get an almost homomorphism that is not close to a true homomorphism. This is again related to what you asked. So to get examples of non-trivial almost homomorphisms, which are not close to homomorphisms, you can, the first attempt would be to try to get a quasimorphism and then exponentiate it. Then we can construct a sequence of almost homomorphisms with Van effect and constant distance. This is again an exercise, but the hint, as I said, is you take the non-trivial quasimorphism and just take the exponent. So this, as you see, the exponent lands in U1. It's just a circle. Okay. So final remarks on just this part is that based on all this I have said, we can make some first small conclusions, which is that if gamma is a lattice of rank 1, then it is not U1 stable, and therefore not UN stable either, because you can just embed U1 and UN. And how did we get this? Well, a non-trivial quasimorphism. In fact, the Fujiwara's result shows that the comparison map is not injective for a lattice of rank 1. So we just use that result here. The other is if gamma has high rank, that is, when I say high, it's usually just 2 or higher, then C is injective and H2 bounded is finite dimensional, and gamma is U1 stable. So far, I've only told you one direction. That is, if there are non-trivial quasimorphisms, if C is not injective, then you know for a fact that it's not stable. But there's actually a result in the other direction too, with some stronger conditions. That is, it's not enough that C is just injective. You also need the bounded cohomology to be finite dimensional. I don't want to get into this right now because that'll take us in a different direction. So the moral of all of this was that at least in the first step, in the toy setting of U1 or R, you can do things very explicitly because you get co-cycles and co-boundaries and you can take the exponents and life is good. So the real question now is, what about UN? And what's stopping us from doing the same for UN? And that's the next part of what I want to talk about. So I'll first erase the board. So any questions so far? We don't know anything. I can't recall anything about hyperbolic groups. What I know for hyperbolic groups is that the comparison map is surjective. But that doesn't really help us with the question of stability as such. I think there's a theorem of Miniev which says that the comparison map is surjective. We want injectivity. Any other questions while I rub the board? No, I think it's Gromov hyperbolic. I am not sure. What does Fujiwara say? It says for H2 is infinite dimensional. And is the comparison map injective? Well, off the top of my head, I can't. Okay, so life was nice for U1. And the reason for that was that when you take the log or exponent and you go into the Lie algebra, the Lie algebra is just R. So there's nothing much happening over there. The question is, what can you do for maps to UN? In fact, this was actually done, and this is the first paper in this topic, which is a result of Kashtan, which is much stronger than what we need for UN, which is that amenable groups are U stable. I'll say what U is. U is the family of unitary operators even on Hilbert spaces. When infinite dimensional works, that's Kashtan's result. But we'll be dealing only with finite dimensional n. So, but and what's the proof? At least the proof sketch. Like what is happening here? Well, the proof idea is the same as what we tried to do before, which was an averaging argument. You again take something like the defect. So you have, you start with phi, you define psi from gamma to un. So phi is the epsilon homomorphism you start with. You define psi, which is the averaging. Let's say phi of g conjugate phi of x g dx. This is what we essentially did even in the U1 case. You just took an average, but over there, the average instantly becomes a homomorphism. Psi becomes a homomorphism in the U1 case. But over here, what happens is psi is not exactly a homomorphism, but psi has defect, something like 3 epsilon square, and psi has distance around epsilon plus some 3 epsilon square from. So in the what we did in the U1 case, if you do the same thing for amenable groups here, just take the average, you do not get a homomorphism, but all is not lost. You reduce the defect. That is, if epsilon is small, now the defect, instead of becoming 0 as in the abelian U1 case, becomes 3 epsilon square. And the distance is still epsilon away. So Kashtan's method was keep doing this again and again. You start with your epsilon homomorphism, do this usual averaging, you get reduced defect. So do it again. Defect goes from epsilon to epsilon square to epsilon to the 4, and ultimately you'll converge towards a true homomorphism, defect 0, and you're not going very far from what you started, because at each step the distance is still linear in the defect of what you deal with. So this hints that maybe you can come up with a cohomology theory that captures this sort of phenomena where you don't have cocycles, but maybe you can have cocycles up to something smaller. And then if you have that cohomology vanishing, then you can independently keep doing this and get a true homomorphism. That's the general idea. But for us to be precise about this, it helps to sort of reformulate and rewrite many of these notions in terms of asymptotics, because you have a 3 here and epsilon goes from epsilon to epsilon square. You want to write it in a more elegant way. So for that, this is simply a rewriting of the definitions, which is a sequence Pn from gamma to some ukn is an asymptotic homomorphism if the defect of phi n goes to 0. And similarly, a sequence Pn is asymptotically close to homomorphisms if the distance of Pn goes to 0. That is, there exists some psi n sequence of homomorphisms so that globally the distance goes to 0. This rewriting is just so that we can capture this sort of reducing defect in some big O notation, for instance. So now in this language, if you just want to abstract out what happens with Kashtan's method and what you can hope to get is this defect diminishing is what you want. That is, gamma has a defect diminishing property if for any asymptotic homomorphism, Pn, there exists some set of maps psi n such that the defect of psi n is much smaller than the defect of phi n. And the distance of Pn and psi n is still of the same order as the defect of phi n. So this looks like a slightly weaker notion of stability, right? Which is you're not asking for an asymptotic. You're not asking for a family of true homomorphisms that are close to this asymptotic homomorphism. You're saying, okay, at least can I reduce the defect from defect of phi of n to something asymptotically smaller, but not moving very far from what you started with. And Kashtan's method implemented this is just an abstraction of what we get in Kashtan's averaging thing. So now if you have this definition, then this does give you stability, because it's the same argument that I said before, which is do this again and again. You're going to reduce the defect by an order of magnitude at each step while still moving linearly in the defect. So if you start with a defect epsilon, then next step the defect will be epsilon square, epsilon cube, dot, dot, dot. So all on the whole will be like less than 2 epsilon or some constant times epsilon. On the other hand, the distance will also be, this is the distance. So at each step, you're moving epsilon, epsilon square, epsilon cube away. So on the whole, you'll move some constant times epsilon away. But the defect actually goes from epsilon to epsilon square to epsilon cube, or epsilon power 4 all the way. So this defect converges to 0. So since the norm is closed, you don't have any problem with convergence here. So the idea is that we have the slightly weaker notion, which is still good enough. So why do we define this weaker notion? Is because this is something we can actually try to implement in cohomologically. So what I mean is, yeah. No. See, the defect of psi n is still order of defect of phi n. So if you ask for a homomorphism, that's just a question of stability. But we weaken the requirement apparently so that we can capture it in some way. So just one more technical way of doing this, which will be much nicer, is instead of asymptotic homomorphisms, we are going to deal with ultra products, so that you can combine this whole sequence into one object. This will be nice to just capture it as homomorphisms. So what I mean is, if you take some non-trivial ultrafilter omega, and then you just take the ultra product of all of these phi n's. So you'll get something like omega of phi n. So what will this be? This will be a map from the ultra power of gamma to the ultra product of these groups. So why I do this is, now if you are going to quotient out all sequences that go to 0, so which we call infinitesimals, this is actually a true homomorphism. This is just a presentation thing. What I'm saying is, if you deal in the language of ultra products, you can actually talk about infinitesimals being objects instead of just sequences that converge to 0. So I'm assuming that people at least know the basic definitions of ultra products and filters, right? So in this language, what happens is that this is, I think Alex was hinting at this yesterday in the diagram, which is, so this K was an additional annoying thing. So phi n was a family of maps from gamma to UKN. Why I don't write n is, you could ask why don't I just write UN? But UN, you think of it as just 1, 2, 3, 4, 5, 6. Here it's just some sequence of maps to some finite dimensional unitary groups. So in yeah, it's just set of some u of some numbers. That's it. You shouldn't think of this as n because you'll think of it's a u1, u2, u3. It's not necessarily that. Okay, so this is the formal algebraic ultra product. So if you have some family of objects xn, just some family of objects, so it's a very formal product. You just take the product over the entire family and you make two elements equal if they agree on almost everywhere with respect to the non-principal ultra filter. No, it's almost everywhere with respect to the ultra filter. So you have this ultra filter of n, right? So what is this? You have xn, two objects xn and yn are equal if the set n such that xn equals yn is in the ultra filter. So why? What's the nice thing about just rephrasing asymptotics in terms of ultra filters is that now a sequence just collapses to one function from the ultra products, between the ultra products. And another nice thing is that you can quotient out sequences that go to 0. It's a tangible object in this universe. So infinitesimals are just elements of this that are infinitesimally close to the identity. For instance, okay, think of it as the real numbers, right? R is just real numbers. You can take the ultra power of R. So this, you should think of it as just sequences over R. It contains infinities and infinitesimals. And you can talk about bounded sequences. You can talk about infinitesimal sequences. So sequences that go to 0 actually appear as objects here. And you can actually quotient out R bounded by R infinitesimals, and you'll just get R again. So these are some standard notions of non-standard analysis. So, and what I'm doing here is writing it this way allows me to see that the question of stability actually looks like a lifting problem, because now you have an almost or asymptotic homomorphism here. You quotient out the infinitesimals, this actually becomes a true homomorphism, right? So now the question of stability is just a kind of lifting problem, whether you have this map from star gamma to this object, can I lift it all the way to this? Right? So if you can lift it, that means there is some sequence of homomorphisms which are infinitesimally close to what you started out with. This is a way of just putting together all this information in homomorphism lifting problem setting. That's it. Star gamma is the ultra power of gamma. It's just sequences of elements of gamma identified up to the ultra field. How much time I have? Oh, okay. Okay. But anyway, I'll continue tomorrow, but I'll just, maybe I'll quickly end with, no, I still have 5 minutes. Okay. So this is the general setting of the question of stability. The reason, so if you want to interpret defect diminishing in the setting, it's even nicer. You have a lifting from UKN modulo those that are of order epsilon to you ask if you can lift it all the way to those that are smaller than epsilon. And so this is a question of defect diminishing. Now, why is this nicer? We saw that this is equivalent to that just by repetition. But this is nicer because this O of epsilon modulo O of small o of epsilon, that is this, this kernel of this lift is abelian. And here you use the submultiplicativity of the norm. For instance, if you take just 2 elements of O of epsilon, that is epsilon away from identity, and just take this a b minus I. You just write it out, you'll see that this is equal to ab minus ba. This is equal to a minus I times b minus I minus b minus I, a minus I. Now from submultiplicativity of the norm, this will actually be like 2 times a minus I, b minus I, and this will be epsilon epsilon, which is 2 epsilon squared. So while we can cast the whole stability problem as a lifting problem by collapsing it with the ultra product, if you have a submultiplicative norm that you work with for the distances, this lifting problem can be made to have an abelian kernel. In fact, this going from epsilon to epsilon square because of submultiplicativity is sort of hidden in the Kashtan's averaging step as well. Even over there, if it were abelian, you'd go from epsilon to 0. But because of this non-commutativity, and you can only get some inequality, and that inequality actually appears here. The submultiplicativity allows you to go from epsilon to something like epsilon square because this quotient is abelian. So this actually motivates, or rather, this is how you can hope to construct a cohomology theory, which is, since I don't have much time and I'll continue tomorrow, I'll briefly just tell you what the idea here is. You again, so how did we do it for U1? You had phi, which was an epsilon homomorphism, and you said, okay, you take the logarithm, go to the algebra, you get a quasimorphism. That quasimorphism, when you take d of that quasimorphism, you get a cocycle. It's a bounded cocycle. You want it to be a bounded coboundary, right? Over here, you in spirit, you're going to do something similar. You again have an epsilon homomorphism to un. You take the log of the defect, you will get some function which is not exactly a cocycle, but it will be a cocycle modulo epsilon square. Right? Initially, or there it was like d1 of f was epsilon, you'll still get a true cocycle. But here, since everything works only up to small o of epsilon, so everything can be done up to an order. So you'll get a cocycle modulo the infinitesimals or epsilon square. So you have to formulate the entire cohomology theory, which captures this, that formally try to write the functions in terms of the ultra product, talk about the bounded and infinitesimal elements, and say that, okay, now we'll deal with cocycles up to infinitesimals. And we want it to be a co-boundary up to infinitesimals. And if you can have that, you will have the defect diminishing property, which was the intermediate step. And if you have the defect diminishing property, you will have stability. So the whole goal of all of this was to somehow combine the ideas of Kashtan's original method, at least observe what it gives, ignoring the fact that it was just averaging, what it gives, reason out that, okay, you can try to abstract that epsilon to epsilon square using the submultiplicativity of the norm, and then build a cohomology theory which always works bounded modulo infinites. So I'll continue with this tomorrow, and we'll see a lot. Into the Lie algebra.
So that will be multi-value.
Well, since you're already close to epsilon, you don't have to worry about branching or anything. It's so in the U1 case, it was like everything was happening in a small neighborhood, right, from here to here. In the UN case, you think of it as everything again happening in a small neighborhood, but now you have to take epsilon and something like small o of epsilon. So
other questions? You kept saying that the defect diminishing is like a weaker version of stability, but then it seemed like you're trying to convey that it's equivalent, or
yeah.
Okay.
It's sort of splitting the question of stability into many smaller steps, which can still be combined to get stability, but these steps give you abelian kernels which can be built cohomologically.
And it's weaker, but it's also stronger, right? It's the linear type stability,
Yes,
right?
yes,
Okay.
yes. Yeah, sure. I probably didn't. So let's, instead of calling it big O and small o, just call it bounded in terms of epsilon. That's a better notation. So yeah, you should think of this as O epsilon. I didn't want to introduce a notation in the last minute, so I wrote it like that. This is like UKN, small UKN, elements of, this is the space, right, UKN. These sequences such that UKN minus identity, this norm is O of epsilon. Here epsilon is actually an infinitesimal, right? So what you mean by small order of O of epsilon is that, so this is okay, right? Yeah. Yeah, epsilon is like the sequence which is now an infinitesimal. Small o of epsilon is the same thing, but small o. So what is big O and small o? It's A is equal to small o of B if A by B is an infinitesimal. So it's basically the same idea of this big O small o notation, but in a much more precise sense with ultra products. It is A by B is an infinitesimal.